because integration is the reverse process of differentiation, we can use the derivatives of the inverse trig functions to get the following integral formulas. So if we want to integrate 1 over the square root of 1 minus x squared dx, so if you remember, this was the derivative of the inverse sine function, and so that means that the integral of this should give us back the inverse sine of x plus some constant. And then similarly, the integral of 1 over 1 plus x squared dx, so if you remember, the derivative of inverse tangent was this thing, so that means if we integrate, then we get back inverse tangent of x. And then finally, if we integrate 1 over the absolute value of x, square root of x squared minus 1, this was the one involving inverse secant, and so this is inverse secant of x plus some constant. We can actually take these three integral formulas and generalize them a little bit, which will make it easier to compute integrals without using u substitution. So instead of a 1 here, let's say it's some constant, just suppose the integral is the form 1 over the square root of a squared minus x squared. So say there's some constant here. If you use the u substitution to simplify this integral, you'll see that the antiderivative is going to be inverse sine of x over a plus c, the integral of 1 over a squared plus x squared. Similarly, if you use a u substitution and apply this formula, you get 1 over a inverse tangent of x over a plus c. Finally, if you put a constant here, you get the integral of 1 over absolute value of x, square root of x squared minus a squared. Again, a u substitution, and using this formula will give you 1 over a inverse secant of the absolute value of x over a plus c. I ran out of space. Okay, so let's look at some examples of computing integrals using these formulas. Okay, so let's try to compute some integrals. So the first one is an indefinite integral, so we just need to find the antiderivative. So what we want to do is we want to put this integral into one of these forms. So we'll see that it's going to be this form here. Okay, so we want to factor out the 9 so that the coefficient of the variable is equal to 1. So this is equal to the integral factor out the 9 from the denominator. This becomes 4/9. This is t squared. Because the 2/9 is a constant, I can pull that all the way out. And then 4/9 is the same as 2/3 squared. And now this integral is exactly this form here. So this is equal to 2/9. So a is equal to 2/3. So that means 1 over a is equal to 3/2. inverse tangent x over a, but because the variable is t, we have t. Because again a is in the denominator, we need to flip the 2/3, so you get 3/2. So simplifying this, 2 over 2 cancels out. 3/9 is 1/3. So this is the antiderivative. Okay, so now let's look at the second integral. So again, we rewrite the integral into a form that's easier to compute. So we factor out the 4. Then the square root of 4 is 2. We'll pull that all the way out. So we got 1/2. The integral from 0 to 3/2 dx over the square root of 9 minus x squared. But 1 over a squared minus x squared is this integral here. So the antiderivative is inverse sine. And here a is equal to 3, because 3 squared is equal to 9. Evaluated from 0 to 3/2. Plugging those numbers in. So evaluating 3/2, you plug it in for x. You get the 3's cancel out and you get 1/2. And if you plug in 0, you get 0. Inverse sine of 1/2 is pi over 6, and inverse sine of 0 is equal to 0. So the answer is pi over 12.